Hello students, today we are going to learn how the accelerated particle is going to radiate. In the last lecture we have seen that the charged particle with constant velocity has some electric field and a magnetic field, but it cannot radiate the power in the radiation zone, or it has no radiation field. So today we will discuss the particle which has collinear velocity and acceleration, which means the velocity and acceleration are in the same direction. So the collinear means velocity and acceleration are moving along the same line, they are along the same direction. So the acceleration produces this kind of electric field due to a charged particle. This is in the Gaussian unit. You can also convert this into SI units as we discussed in the earlier lecture or earlier video. So we can put beta is equal to V by C. Even we can substitute U bar. We can substitute like this R bar, which was R bar minus beta bar R. And then we can get again in the SI unit. But we will not do that because we are interested only qualitatively how the radiation is produced due to the accelerated charged particles. So the next step to this will be, we will expand this bracket and we will multiply this with beta dot. So what is beta dot? That is the acceleration. We had beta is equal to V upon C, or beta bar is equal to V bar upon C. So beta bar dot is nothing but V bar dot upon C. V bar will be our velocity and therefore its time derivative will be the acceleration. So basically this quantity beta bar dot represents the acceleration of that charged particle, while beta is just the velocity of that particle. Now when we expand this, we will get this term R bar cross beta bar dot minus R beta bar cross beta bar dot. Now as we have considered that velocity and acceleration are moving along the same line, they are collinear, and therefore their cross product will be equal to 0. So the second term will get cancelled and we will get only this term. Therefore this is E due to electric field due to acceleration of charged particle. Now see, we have already seen that velocity cannot produce the radiation, so we are ignoring the electric field due to velocity, but it can be there, it is still there, but we are not calculating that. We are just calculating what is the electric field due to the acceleration of the charge. Now here you can see there is a vector triple product. So we know how to deal with the vector triple product. We use the back cab rule. If you don't know, I will quickly tell you what is back cab rule. If there is cross product of three vectors, let's say A bar cross B bar cross C bar. So this is a bracketed term. So we have to solve this first, and again there is a cross product with A bar. So we solve this using the rule called as a back cab. So BAC minus CAB. Now what we have to do, we have to give the vector signs to all, but you see here this is a cross product, so this quantity is a vector, so we will get a vector. But in this case the cross products are converted into the dot products, so we will get A bar dot C bar and here A bar dot B bar. So A bar is common in the dot product for both sides, but once B has come out, then C has come out. So this is you can remember this as a back cab rule, and using this rule I have solved this bracket and we got, okay, I will give notation here. Here you can see A and B are same and here it is C. So here we will get BAC back, CAB cab. Okay, so you can note here R bar is also A bar as well as B bar. So we get here B bar into A bar cross A bar dot C bar minus C bar into A bar dot B bar, right? And I have kept this bracketed term as it is. I have not written, okay, but it is there. We can write this bracketed term into the left side of r bar, because this bracketed term is just a scalar quantity, so we can write on either sides of the vector, either left or right. And in this case also we can do the same. So r bar dot r bar, the dot product of the vector with itself, is the square of that product, and which is scalar quantity, and that's why we write here r square, and here we have just rearranged the terms, and this cube as it is, this e by c as it is. So let us call this equation number 1. We know this is a pointing vector. Basically it is e bar cross b bar, and the subscript a denotes that it is due to the acceleration of charged particle, and this is constant which we will use in the Gaussian system. If it is SI system, instead of c by 4 pi we had to use 1 upon mu naught, okay, but instead we are using c upon 4 pi because this is in the Gaussian system. And therefore we also have seen the power per unit solid angle is given by, this is nothing but s bar dot dA bar, okay. So this dA bar I have replaced with the n cap r square. So the area is r square and the direction is n cap. Now in general we know the spherical area is 4 pi r square, but you can see here 4 pi is not there. This is because this is because Gaussian unit, and we are not taking the complete sphere. We are just taking some portion of that area, and that's why it is just r square. We have separated the direction and the magnitude of that area vector. So we have to find out this term, and we will get s bar from this term, and e bar and b bar we will get from this equation number 1. So we can put e bar and we will get b bar also. I will show how, but let's first look at this. What is omega? Here we have written this dp by d omega. So what is omega here? The omega is the solid angle, okay. So what is solid angle? We generally know the angle which we measure in the two-dimensional plane. So the solid angle is the angle in the 3 dimension. It is 2D angle, but we measure this in the 3 dimension, like the cone of ice cream. So the angle at that cone is nothing but the solid angle, okay. So we are measuring that solid angle, which is nothing but d omega. So the power reaching at this point, let's say P, or let's say in this area dA, that is dP upon d sigma. That is power per unit solid angle. So instead of magnetic field, we have substituted n cap cross electric field. Generally we know in the free space, magnetic field and electric field are perpendicular to each other, and the wave is also propagating in the perpendicular direction to both of the directions. So here the n cap is the direction of propagation, and that's why n cap cross e bar will give the direction of b bar. And so we have substituted this. Again we can use the back cap rule and solve further. We can get, if this is b bar into a bar dot c bar. So a and c here both are same, therefore it is squared, and then minus c bar, which is ea, into a bar dot b bar. As I have discussed earlier, n cap and e bar are perpendicular to each other. The dot product between the two vectors is always 0. So this term is cancelled, only first term, and obviously the term outside the bracket is also there. Here you can see n cap and this n cap are having dot product, and the dot product of the quantity itself is the square of that, and the magnitude of unit vector is always 1. We can ignore n cap dot n cap, or that is just 1 basically. So we are getting the power per unit solid angle is equal to c into 4 pi e a square r square. Let's call this as equation number 2. Now we have value of Ea in the equation number 1. So we will substitute that value in this equation. Now we can see here the value of Ea, that is the electric field due to acceleration of charge. So we have to substitute this, and we need not to write this quantity again and again, so we will substitute the bracketed quantity as k. So here k will be the scalar term, which is the bracketed quantity, and it is nothing but r minus beta bar dot r bar. Okay, you can see this quantity here. So we will just replace k in the later in the derivation. From equation number 1 and 2 we will get this term. Okay, and again I have written here the substitution, k is equal to r minus beta bar dot r bar. So the power per unit solid angle will become this term. This is EA and its square. In the EA there is itself the quantity E by C, so its square will be there, and 1 C is already here, so 1 C will get cancelled out from here. We will get 1 C only in the denominator, and then we will solve the brackets. So E square I have written as it is, this R square I have written here, there are 4 pi C, and then k raised to 6, because there was k cube, there was here there was k cube, and then bracket square, so it will become k raised to 6, and then the square of this term. So we can write this as a minus b bracket square. So we will get a square plus b square minus 2ab. So we have just substituted these terms in such formula. You can observe here this r bar dot beta bar dot bracket square is quantity appearing again here, because here you can see r bar dot beta bar dot into again r bar dot beta bar dot. Both are scalars, so here is also a square, here is also a square. So both are same, but the coefficients are different. Here is +1, here is -2. So we will get final -1. So we can get r raised to 4 beta bar dot minus r bar dot beta bar dot bracket square into r square. Again from this square bracket we can take r square common outside. So we will get r raised to 4. It will become r raised to 4 outside the bracket. This r square and this r square. So here it will become r square, and here this bracket will be as it is. And so this will be some next step. Now taking the r square beta dot square common from the bracketed term, we will get, so here it was r square beta dot square, so I have taken this common, but here is no r square beta dot square, so it will get divided to this term, and again we can get r raised to 4 into r raised to 2, that is r raised to 6. Here I have taken beta dot square here, and if we solve this, this term is nothing but r bar dot beta bar dot, which is r beta dot cos theta, and its square, so it will become cos square theta r square beta dot square. So in the denominator is also there is r square beta dot square in numerator also, so these two terms get cancelled, and we will get 1 minus cos square theta, which is nothing but sin square theta. So we have got the equation number 3. All other terms are kept as it is. Now you can see here, this is the power reached at some point P at very large distance r from the source, and you can see here the term r raised to 6. So is it proportional to r raised to 6? What does it basically mean? So if my r increases as I go away from the source, the power is increasing. So does it seem logical? No, it is not logical. What we are seeing is not true. That is not exactly proportional to r raised to 6, because there is one term in the denominator which is k raised to 6, and it itself contains the term r. So there is also in the denominator is also there is term r raised to 6, in the numerator r raised to 6. So those terms will get cancelled, and we will see later. But remember, this term here is constant for constant r and theta. This means if I fix some distance, here is some v, and this is angle theta. So for this angle and for this distance r, charge is constant, c is constant, and k will be constant for constant r, and therefore constant r and as well as constant v. But we know the v is not constant term. Still we are using this because we are measuring this electric field or this power at instant of time. This is instantaneous measurement, and therefore we can take it as a constant. Okay, so this is constant I am getting. So let's call this as equation number 3. Okay, so that was the equation number 3 was the general equation. Now I want to calculate the power radiated or received at that point for a particular time t0. Then we will get the short interval of time. We use calculus for that, differential calculus. So we can get dp by d omega dt naught is equal to dp by d omega at dt. Okay, so at t naught and at dt, that term will be constant, and I am taking this dt to this side. So I have skipped one step. Okay, so there was a differential step there, but I have skipped that, and now I want to find out this term dt by dt naught. We know t is equal to t minus, okay, t is equal to t naught minus rc. So differentiating this term, we will get dt is equal to dt minus dr by c. So again dividing this term by dt naught, we will get dt by dt naught is equal to 1 minus dr by dt naught into 1 upon c. So I have just kept separate, and this is nothing but the speed, and the speed divided by c is nothing but beta. So dt by dt naught is nothing but 1 minus beta, or I can write this beta term as beta bar dot n cap, because beta is itself a vector. So I can write this, and it is in the direction of n cap. So basically both quantities are the same. Now what will happen? I will put this term in this. So I will get this term, and substituting this from equation number 3, I will get e raised to 2 r raised to 6 beta dot square divided by 4 pi c k raised to 6 sin square theta into this term 1 minus beta, okay, or beta bar dot n cap. So we will find out now what is k. So from this equation number, let's call this as 3b, which is 1 minus beta bar dot n cap. So we know n cap is nothing but r bar divided by r. If I substitute this in term of this, 1 minus beta bar dot n cap is equal to, substituting this, we will get r minus beta bar dot r bar divided by r. So this was the initial value of k, r minus beta bar dot r bar. So this is nothing but k by r. So substituting this, we will get k is equal to r into 1 minus beta, or beta bar dot n cap. So we will substitute this, and you can see there is a power 6. So this will also get power 6, r raised to 6, and the bracket raised to 6. This r raised to 6, this r raised to 6 will get cancelled, as we have discussed earlier. And then here is also 1 minus beta, here is also 1 minus beta. So that term will get cancelled from numerator, and here the power will reduce by 1. So it will become 5 raised to 5. And this is nothing but the power per unit solid angle reached at some distance r. Again we will resubstitute that beta bar dot n cap is beta. So this is nothing but the power reaching at solid angle omega at time t0, because we have specifically substituted for time t0. So let's call this as equation number 4. Till now we have solved this for some particular solid angle. Now we want to derive this for all over the spherical area. So we will integrate over the solid angle, and this solid angle is nothing but the area, okay, because this is 2D angle. So the area is nothing but sin theta d phi d theta, or sin theta d phi. So this is in the r theta phi coordinates, which is polar, spherical polar coordinates. Now for this angle measurement, only angles are changing. So r is not changing in this case, speed is not changing because we are measuring this at some instant of time. So beta is not changing, beta dot is not changing. So all other terms are constant of the angle, and that's why we can take it outside the integral. We know for a complete measurement of area, the limits of phi are from 0 to 2 pi, and the limits of theta are from 0 to pi. If we are measuring the volume, then the limits of r will be from 0 to infinity. Okay, but we are just measuring the area, and therefore These are the limits of the integration, and this is very simple. You can solve this very easily, and we will get the integral of this is 2 pi and this is 4 by 3. So pi and this pi will get cancelled, this 4 and 4 will get cancelled. So we will get 2 by 3, then e square by c, then beta dot square by 1 minus beta bracket us to 5. So this is the power radiated by the accelerated charge at time t naught. This is total power radiated at that instant of time. So we are not integrating over the time. This is just at some instant we are measuring. Now look at the terms in this equation. There is no dependence of r. Okay, so this is constant of r. Then power is constant. Even if the r is changing, then also p is not changing significantly. So what does this mean? Suppose we are on the earth. Let's assume this is the earth and the sun is at this location somewhere, as this is far away. So I have drawn like a point size compared to the earth. But what I wanted to say, the radius here is r, let's say the distance is r, and here it is r naught. Here it might be some capital R, let's say. Okay, so the distance reaching over the earth's surface is not constant, but still the power reaching at those points will be the constant. This is irrespective, or this is independent of the distance r. It might be changed due to the atmospheric absorption, because earth has some atmosphere. But if you go to the moon, the power reaching at those surfaces will be the same. In some previous lectures we have seen static charges do not radiate. In the previous video we have seen the charges with the constant velocity also do not radiate. But today we have seen that the particles with some acceleration, the acceleration may be or may not be constant. I am not bothering about that, because you can see here clearly there is some power. Okay, there is some power here. This beta dot is acceleration. So it may be changing or it may not be changing. Beta is obviously changing, but we are measuring this at some instant of time. So this is instantaneous velocity beta and instantaneous acceleration beta dot. So it just depends on that.